Swayam Prabha. Digital India. Educated India.
Having described the kinetics of particles, now we will discuss plane kinetics of rigid bodies. We have not taken any lectures on the kinetics of system of particles because I thought that the same thing gets covered if I describe the kinetics of rigid bodies. Rigid body is after all a system of particles in which continuous distribution of particles is there. So instead of algebraic additions, here you will get integrations actually. Same thing can describe the kinetics of system of particles, but instead of integration you will have discrete additions. But otherwise the essential thing remains same, procedure is entirely same, so therefore it gets this one covered here. Now a rigid body is composed of several particles. Its equation of motion can be obtained by applying Newton's law to individual particles and integrating the combined effect. So you have got that so we have got a lot of particles here and they are of that different this one. We can take a small that particle of that size dm, where dm is tending to 0. That means rigid body is composed of then infinite number of particles. However, its mass is finite because product of mass into a product individual particles mass is 0. So 0 multiplied by infinite can still give you a finite number. That's how we do that thing. So therefore here that now we take a small particle of mass dm, which is very small differential element. Now the mass center is denoted by g. And if we take any axis system like Ox, Y, Z, then O times this O to G, this distance is R bar and this is O to dm, that is R. So this distance is R and then G to dm, this distance is there. Now here we apply Newton's law. Now let us consider a body whose mass center G is located by the position vector R bar. Then R bar is actually R dm divided by m, where this is R we have written by bold letters, that means it is a vector. So R dm divided by m, m is the total mass of the particle body and R dm this is so this is the mass equation of the mass center we have integrated. This is based on the continuum hypothesis. We assume that all the particle, this whole body is in a continuum. There are no voids in between the particles. That is our assumption and we have been able to integrate. Now we apply Newton's law for a particle of mass dm, and then we have df plus df is equal to dm times r double dot. For that particle, the force acting on that particle is df. It is the resultant external force acting on the particle, and df is the resultant internal force acting on that particle. That is equal to dm times r dot dot, because r is the position vector of that particle with respect to that outside inertial frame of reference. O is some stationary point, so r dot dot will give acceleration, and you will have df plus df is equal to dm into r dot dot. Integrating, if we integrate both sides of these equations, so we integrate df, also we integrate this thing df, and here we integrate dm times r dot dot. So this is equal to basically, if we integrate dm r dot dot, that is equal to m into r bar double dot. Well, because we have equation 1 says that r bar is equal to integration of r dm divided by m. So we get df plus integral df is equal to dm r dot dot, that is mass times r bar dot, where r bar is the distance of the center of gravity from the fixed point, and m is the total mass of this thing. Now if we integrate df, we get F net. Well, F net is the net external force, and if we integrate df small f, then this will become equal to 0, since internal forces balance each other. So basically the internal forces will balance each other, and therefore this is the thing. Now internal forces will balance each other. So this is internal forces will balance each other, internal forces. Now the resultant of the external forces acting on the body equals the mass m of the body times the acceleration a of its mass center g. In that case, you get only this equation, that resultant of the external forces is mass times the acceleration of the mass center. Now it has to be noted that the acceleration of all particles in the body need not be same. The body in this animation is moving with acceleration. So you can see the animation that this is undergoing rectilinear motion. That means this body is moving in a straight line, and in that case all particles are moving with the same velocity and same acceleration. So therefore, if we talk about the acceleration of mass center or of any other particle, that doesn't matter. However, in the other case, the acceleration of, in this animation, this disk is rotating. Now the acceleration of all particles is different. Particle O is not moving, so its acceleration is 0. Particle A is having the maximum acceleration. Mass center is O. So although the particles, there is a acceleration of body, that means some particles are having acceleration, but overall that mass center is not having acceleration. So therefore net resultant force must, external resultant force must be 0. That condition is there. Now so the angular momentum, now let us talk about the angular momentum. The angular momentum of the mass system about the mass center g is the sum of the moments of the linear momentum about g of all particles, and is given like this. This is the, suppose you have a fixed point O here, and this is a mass center. This distance OG is r bar, and from G to dm I have denoted by Ri, and then this capital Ri, and then small Ri is the absolute displacement vector of dm with respect to O. So you get Hg is equal to Ri class dm Ri dot. So this is the angular momentum about mass center, about g. So but here I have taken the absolute velocity. So dm, that means you write the absolute linear momentum and cross product it with Ri, that means distance from the mass center. You get then expression for angular momentum. So Hg is equal to Ri cross dm r dot I. If you differentiate this expression with time, then you will get h dot g is equal to r dot I cross dm r dot I plus Ri cross dm Ri dot dot. We applied the product rule of differentiation. Now it can be easily shown. Now it is not, although if the body is moving in a translatory mode, then Ri remains in the same direction and r dot I is 0, because the distance between the particles of the rigid body cannot change. However, if the body is doing rotation, in that case r dot I need not be 0, but this can be very easily shown that actually this first term, that means r dot I cross dm Ri will be equal to 0 and only the second term will remain. Now this can be shown like this, that if we can write Ri, this is like this, if we say that this term Ri dot cross dm Ri dot is equal to, this is integral Ri dot cross dm, this will be r bar dot plus Ri dot, like that we have decomposed. Then this will become, the second term will obviously become 0, because cross product of r dot I with r dot I is 0, and the first term becomes 0 because by the definition of the mass center. So you have Ri dot dm can be taken, because it is a scalar quantity, you can take it like this. Then what happens, you are left with r dot I cross dm and r dot, but this is 0 because we have that equation number 1. Here it was shown that r dm. So if you can show that, if you have taken the, if you differentiate this, obviously this will come out to be 0. So that way it can be shown. So first term that becomes 0 and the second term remains Ri cross dm into Ri dot. Thus we have, hence we have h dot g is equal to Ri cross dm into Ri double dot, and that is equal to basically Ri cross df plus df, because here df is the external force acting and this is internal force acting. So dm times Ri dot dot, here you can apply the Newton's law and you get this thing. Now these are the internal forces, so their movement will obviously be 0 and you are left with Ri cross df, and that will equal to m net. So thus the resultant moment about the mass center of the external forces on the body equals the time rate of change of the angular momentum of the body about the mass center. So you have got h dot g is equal to m net. Now you consider a body subjected to a number of forces. Now we can consider the subjected to number of forces as shown in the free body diagram here, that we make the free body diagram. In the free body diagram we will show only the forces are the forces acting on the body, that is called free body diagram in that. And then so we see that a body, arbitrary body with mass center g, we have shown just 4 forces and one point has to be noted that these forces can be replaced by an equivalent force and moment system. So the body is subjected to, so we can take the effect of all the forces here and we can find out F net, that resultant is passing through G, and then we have one couple mg net, because we discussed in the first lecture itself that the force system can be replaced by one resultant force and then the net moment. So this is like that. Now so then we can obtain the kinetic diagram. Kinetic diagram shows basically the inertia forces, you can say, that mass into acceleration and in mass into linear acceleration and mass into angular acceleration, that moment of inertia into angular acceleration. So kinetic diagram is obtained by applying Newton's law. Kinetic diagram of the body is shown here. Now we can see that net force is in the some direction, in the same direction mass into acceleration will be active. Then you have h dot g, that is the angular momentum. That angular momentum is also shown and it is in the direction of your mg net, because we have established that equation that rate of change of angular momentum will be in the direction of m net. So you have got here rate of change of angular momentum in this direction. Now if we consider the plane motion, let us consider the plane motion in this right. The mass center is shown as G, and now we choose any other point. This point is O, which is a fixed point. We take any other point P, which may be on the body or it may be on the hypothetical extension of the body. So in that case, the distance of P to this G is R, that is this distance and fixed distance, and then you have this d small mass dm, that is at a distance of r dash from here, and then we have g to dm is ri, and we can attach axis system at g also, and body may be undergoing translation as well as rotation. In that case, what happens, let us say the mass center G has an acceleration of a and the body has an angular velocity omega is equal to omega k, and angular acceleration alpha is equal to alpha k, both taken in the positive z direction. So this will be alpha k. Now because the z direction of both omega and alpha remains perpendicular to the plane of this one, so therefore we may use scalar notations omega and alpha to represent the angular velocity and angular acceleration. We just can write the scalar equations, that will be enough. Now in this case, if we write, okay, so this is hg is equal to basically ri. If we talk about this one, this hg is equal to ri cross dm, r dot I plus r dot, and this is ri cross dm cross r dot I plus r cross dm r dot. Now this term becomes 0, that because this second term may be written as r cross into dm r with a minus sign, which is 0, since the first moment of mass about the center of mass is 0. Now for a rigid body, the velocity of dm relative to g is r dot I is equal to omega cross ri. So the magnitude of r dot I is omega ri, and it lies in the plane of motion normal to ri. The product ri cross dm ri is then a vector normal to the xy plane in the sense of omega, and its magnitude is ri square into dm. Thus magnitude of hg is equal to omega into ri square dm, that means it is ig into omega. where Ig is a constant property of the body and is a measure of the rotational inertia are resistant to change in the rotational velocity due to the radial distribution of mass about this thing. So this is the about this one, and then you have now mg net is equal to hg, that is Ig times omega dot, or this becomes Ig into alpha. So thus for a rigid body in plane motion, you have two equations of motion. F net is equal to ma, that is a vector equation. It can be, you can have two scalar equation. F net in x direction is equal to mass times acceleration in x direction, and F net and y direction is equal to mass times acceleration in y direction, and mg net is equal to Ig. That is, so these three equations are enough to determine the motion in a plane. We now develop that some alternative moment equation. Now you consider a point P different from center of gravity, and angular momentum of the body about this point P is given by dHp is equal to Ri prime into dm into r, because this distance is Ri prime from here. So this is Ri prime, and that can be written as r plus Ri class dm into r dot. So now this can be written as, this is equivalent to that, like this. The first term may be written as r class dm into r dot is equal to r class r dot dm, or r into mvg, where the vg is the velocity of the mass center. Second term is hg. So now make use the principle of moment. We can also write mp net is equal to mg net plus r class f net, and we know in this case mp net will be h dot g and f net will be equal to mass times acceleration. So therefore r is the vector from P to the mass center g, and a is the mass center acceleration. We already know that h dot g is equal to I alpha, and the class product r class ma is simply the moment of magnitude m times a times d of ma about ap, where d is the perpendicular distance of acceleration vector from that point. So therefore mp net is equal to I alpha plus mad. We can write by parallel axis theorem I is equal to ip minus mr square, because I is the moment, second moment of inertia about the center of mass. So therefore we can write like this, and then it becomes mp net is equal to ip minus mr square into alpha plus ma times d, and this becomes equal to ip times alpha plus r class ma. So if we write that ip into alpha in the vector form, that means just put k, then we can write that this, after simplification, this will be ip times alpha k plus r class mass times acceleration. So in this case we can certainly say that, see, about any point P, the P may be on the body or it may be on hypothetical extension of the body. You have the equation that mp net is ip times alpha, and then you have got r class mass into acceleration product. Now if the P is a fixed point, it is not moving, so this portion goes to 0. So we have mp net is equal to ip times alpha. That means the, just as you find out the equation about the mass center, that moment about the mass center is mg net is equal to ig times alpha, so you get the same way that ip times alpha, so that becomes valid. Or else, so first condition is that P should be stationary, then this is valid. The second is that if AP and R are having the same direction, then also it is valid. Thus we say that this equation, if we write m is equal to general form that O is in any point, and we write m0 or mo equal to io times alpha. In that case, this mass mo is basically the moment about O, and io is the mass moment of inertia about point O. So this equation is valid provided three conditions. This O is mass center, O is same as G, then also it is valid. O is a fixed point, or O is having one acceleration which is in the direction of mass center, because R is the if it is that point is having towards acceleration towards the mass center, then also this equation is valid. Now, so having discussed that kinetics of rigid bodies in plane motion, now we describe the kinetics of body in different modes actually. So first we decide that a rigid body in plane can move in two modes. One is the translation, other is rotation. So any motion can be broken down into two parts. One is the translatory motion and other is rotary motion. In rigid body translation, in plane motion, every line in a translating body remains parallel to its original position at r times. That is the definition. In rectilinear translation, all points move in straight lines, whereas in curvilinear translation, all points move on congruent curved paths. So that means you can have completely straight line type of motion, or you can have a motion which will be in the curved, but still that every line remains parallel to its original position, and therefore this can be called as this one. So now, like I am showing one animation for rectilinear translation motion. See, now here any particle of the body is moving in a straight line. So the particles of here, they are moving in a straight line. Similarly, the particles here, they are moving in another parallel straight line. So this is the thing, that is the example of rectilinear translation. Now go to the next one. This is a curvilinear translation. Here if we follow the any typical particle, say mass center, we will see that this mass center keeps on moving on the curved path. So this is example of curvilinear translation. However, during the motion, any time if you see any line, let us say this particular edge of the body, that remains parallel to itself. So it is not rotating, that angle theta remains same. So therefore omega in this case is 0. So translating body has angular velocity 0 and also angular acceleration is also equal to 0. So that's what this happens. Now so therefore both for translations omega is 0 and alpha is 0. So for translation of a body, F net then becomes equal to mass times acceleration, because that was one equation. This is a vector equation. F net is a vector and that is equal to mass into A, and mg net is equal to Ig times alpha. So mg net is this one. So Ig, now alpha is 0. So therefore mg net is 0. So that means that is now if you take the about the mass center, that mg net will be equal to 0. So in this case these are this point. Now let us discuss the another type of motion, that means fixed axis rotation. Now in the fixed axis rotation, this is the body which is rotating about the point O, and I have shown the mass center G here. This is the mass center G, and then you have got that AT is equal to R times alpha. It is rotating about this point. So angular acceleration is given by alpha, and the tangential, linear tangential acceleration is equal to r times alpha, where r is the distance of O to G. And similarly, the normal acceleration will be directed towards center, that is an is equal to r bar square, where omega is the angular velocity of rotation and alpha is the angular acceleration. Now in this body, let us see what are the equation. Now we consider non-centroidal rotation. That means assume that O is not the center of mass. In non-centroidal rotation, a rigid body is constrained to rotate about fixed axis, not passing through the mass center. Now for a rigid body rotating about a fixed axis O, all points in the body describe circles about the rotation axis at all times of the body in the plane of motion, and all lines of the body in the plane of motion have the same angular velocity and angular acceleration alpha. These type of things we have discussed actually in the last classes. So the normal acceleration an is equal to omega square r bar, and at is equal to r bar into alpha. So therefore these things will hold good. Then the equations of dynamics are basically this. We get always these two equations: F net is equal to mass times acceleration, and mg net is equal to ig times alpha. So thus we have F net. Now F net is equal to m alpha. This is basically a vector equation. We can make out two scalar equations here. One is the F normal net is equal to mr omega square, and F tangential net is equal to mr times alpha. So this is what, and then we get mg net is equal to ig alpha, which is of course scalar equation. Otherwise we can write it as a vector equation also if we attach k bar here. K is the unit vector in the z direction. So since it is same actually both sides, so we eliminate k and we write in a scalar form mg net is equal to ig times alpha. So this is what, that these are the three equations we have got, and by this we can get the required things. Now when you apply the moment equation about g, like you have to apply mg net is equal to ig times alpha, then always remember that you have to account for the moments of the all the forces applied to the body. That means even you have to consider the forces, internal forces which are applied at O. When you make a free body, you have to understand that there are some internal forces at O. These also have to be reaction forces. They have to be taken into account. So this force must not be omitted from the free body diagram. That is the point. Okay. Even if you omit some force which is passing through G, then maybe it is all right, because when you take the moment about G, so that force effect vanishes. But in general you should show all the forces. Now consider the free body diagram of the body. Say for example this thing. So body is acted by these forces and it was fixed at O. There must be some reaction force acting. That force also has been taken into account here, and this is the R and this is G, and this is the thing here. Now now we make the equivalent kinetic diagram here. So this is ig times alpha. This is, we show that ig alpha, and then we show here mass times the tangential acceleration passing through G, and mass times the that normal acceleration. This is basically man. So in the kinetic diagram we will be showing these things, mat and man and ig alpha. So this is a kinetic diagram. From free body diagram one can easily obtain the kinetic diagram by applying Newton's law. You see the resultant force passing through G. You have to transform these forces into a resultant force passing through G, and then you can find out mass into acceleration here. Mass into acceleration vector will be in the same direction as the resultant force passing through G, and then you can find out the ig into alpha because if you can find out the moment of all the forces about G, then you can get this thing. Now we also have discussed in this lecture this equation that if you take any point P, say P is any point, then you get MP net is equal to IP times alpha plus R class mass into AP. Here IP is the moment of inertia of the body, second moment of inertia, mass moment of inertia about the body, but it is about point P, and this is R class MAP. Here AP is the acceleration of point P, not the point G, so it is point P. Then so we get this equation. Now if we are talking about the fixed point O, then we can use this equation instead of P, just write O. You get MO net is equal to IO times alpha plus R class MAO. However, O is fixed, thus acceleration of O is 0, so capital O is equal to 0. Therefore, you get MO net is equal to IO times alpha. So this is the equation for the moment. Now for the common case of rotation of a rigid body about a fixed axis through its mass center G. Now if you have a rotation of a rigid body about a fixed axis which is passing through the mass center G, then in that case A will clearly be 0 and therefore sigma F is equal to 0. Then the resultant of the applied force then is the couple Ig times alpha. In that case it will be simply Ig times alpha, because that is the thing. So this way, so these equations can be used to study the rotation of a body. And now we are going to introduce one concept that is called center of percussion. We tell about the center of percussion here. We have seen that if a body is rotating about fixed point, not passing through its mass center, then the force system on the body may be represented by two forces passing through its center of mass in the normal and tangential direction, and together with a moment Ig times alpha. You see, always in this case, for example, kinetic diagram has been shown. Now from kinetic diagram one can obtain a resultant free body diagram. Here one can see the forces. Since in the kinetic diagram you are having that Ig into alpha, that means the moment should be present here. That moment is equal to Ig into alpha, and mass times At is equal to Ft, and mass times An is equal to Fn. So therefore what happens that if a body is rotating about fixed point, not passing through the mass center, then the force system on the body may be represented by two forces passing through its center of mass in the normal and tangential direction, together with a moment Ig times alpha. The moment may be eliminated if the line of action of a tangential force is shifted to pass from the point Q instead of G. In the same line you join O and G, and then after that you shift, so as shown in the figure here. This point, then the point Q is called the center of percussion. So now I have made another diagram. In this diagram the moment has eliminated. Why? Because there was a force passing through G. I have shifted it in a parallel manner to another point Q on the same line. So now this is in effect this point. If you take the moment about G, you will still get a moment, because the point is not passing, force is not passing through point G. So there is no need to show the force. So therefore this has been shifted, and then this point Q will be called center of percussion. Let me repeat these points because this is very important. Now so this point Q is a center of percussion we have described. Now let us see from another angle. For a general planar motion, we have these equations of motion, that is F net is equal to mass times acceleration, that is this one, and then mg net is equal to Ig times alpha. So these are basically three scalar equations. F net is equal to mass times acceleration and mg net is equal to ig times alpha. Now free body diagram and equivalent kinematic diagram are shown here in this one. Here free body diagram shows the forces, externally applied forces, and also the reaction forces passing through O. G is the mass center, and then the kinetic diagram is this: mass times tangential acceleration, mass times normal acceleration is here, and then you have got Ig times alpha. Now consider a non-centroidal rotation about O, like in this case. Now if we pass a tangential force through G, if the tangential force was passing through G, then mass times At will be equal to F. That is this thing. Now where At is the tangential acceleration, now the angular acceleration is given by At is equal to alpha is equal to At times R. So thus you will have mg net is equal to I times alpha. Now since the force F is passing through G, the moment of that force is about G0. Now if it is so, from where we do mg net, then from where, because we have to balance this, mg net is equal to I alpha. Obviously we get it from O, because there are some points at O, so from that. So from the reaction at the pin, that you know that because it is pinned at O, so we will get that. Now suppose a force F is applied at a point Q, which is at a distance of K0 square by R from O. Instead of that, you know that passing through G, if now we apply to pass through that Q, where K0 is the radius of gyration here about O, that is the moment of inertia about O is given by I0 is equal to mk0 square. So this is given here. So then here now you will have, if you take the moment about O, so you will have that Fq is equal to I0 times alpha. That basic equation about O you have applied. So alpha is equal to Fq by I0. Now we have expression for Q, so it is F K0 square divided by R mk0 square is equal to F divided by mr, and this is equal to F by m into 1 by R, and that means this becomes equal to A by R. So this is hence the tangential acceleration is A is equal to F by m. Therefore the net tangential force obviously must be F only. Thus the force, therefore since the net tangential force is F, and we have already applied the force F here passing through this one Q, therefore hence the force is, therefore this force applied by the pin must be 0. Therefore we conclude that if a force is applied at the center of percussion, tangential force is applied at the center of percussion, then no tangential reaction is developed at the fixed support. We can also conclude that the sum of the moments of all forces about the center of percussion will be 0. That because if you take the moment about the center of percussion, then that is 0. So therefore if we want to get maximum advantage, so sometimes you know batsman will hit the ball. In that case, that if he hits the ball at the center of percussion, he will not feel any reaction at the hand, and therefore that force, impact force, will not be experienced by him, and he can still provide the angular momentum to the bat. Now we discuss, so this is the center of percussion is very important in many situations to find out that what is the center of percussion. Now we discuss the other type of motion, that is called rolling motion. Now this is the motion of a disc or wheel rolling on a plane surface, that This surface may be horizontal or it may be inclined to this one. If the disc is constrained to roll without sliding, the acceleration of its mass center and its angular acceleration are related. Like in the plane, in pure rolling motion, the acceleration of the mass center and the acceleration of angular acceleration will be related. But if there is some slippage taking place, then there is no relation. Now you can consider the different cases, like one you can have balanced disc. A balanced disc is that disc whose mass center and geometric center will coincide. Like if you have a cylinder, then if its mass center is located at its center of the cylinder, then it is called a balanced. But if mass center is at some different, then you know that it is called unbalanced disc. So in that the acceleration of mass center is angular acceleration times the radius, that radius of this one. Because the body is in plane motion, the kinetic diagram of the body consists of a horizontal force applied at the center and a couple. So we can make the kinetic diagram because body is in the plane motion. So we can have, so let us consider this case. Now here this is the plane surface and the cylinder is rotating. This is the contact point C. From this you are having a normal reaction N, and then you are having the mass F. So this is like this, and then it is that there is a weight W is there. So this is G, that mass center is G here. This is W, and this is so what here you will have some frictional force F. So F actually will pass through this, and then you may have some applied force acting here, that is P, and the its weight passes through its mass center G. Now this is equal to that here equivalent kinetic diagram can be shown here. Here the mass center is C and this is G, that is passing through this. So you have mass times acceleration, and this will be mass times R alpha, and this is I alpha. So you have got this one. Now when a disc rolls without slipping, there is no relative motion between the point of the disc in contact with the ground and the ground itself. So the point C is the instantaneous center of rotation. Now you get a friction force F also here, but this force is self-adjusting, means if you apply some force here P, the same amount of resistance is developed here with a limiting value of F is equal to mu s times N. So mu s is the this is the sliding, mu s is the coefficient of friction, and into N, that is Coulomb coefficient of. Now when the disc rotates and slides at the same time, a relative motion exists between the point of the disc which is in contact with the ground and the ground itself, and the force of friction has got the magnitude in this case Fk is equal to mu k times N, where mu k will be the coefficient of kinetic friction. Kinetic coefficient of kinetic friction is usually less than the coefficient of sliding friction. Sometimes it may be as less as that, that means coefficient of kinetic friction may be some 50% of the coefficient of sliding friction. Okay, in other cases also the difference may not be that much, but there is some difference. So you get Fk is equal to mu k times N. In this case, however, the motion of the mass center G of the disc and the rotation of the disc about G are independent. You don't have the formula like V is equal to omega R. These type of things cannot be done, and similarly mass center acceleration cannot be said to be alpha times R. That will be less or equal to mu s times N. Either it will be less tangential friction force, either it will be less than mu s times N, or it will be at most equal, because mu s times N is the limiting value and S is the coefficient of sliding friction. And then you have one relation for geometry, that means A is equal to r times alpha. So you have A is equal to r times alpha, and r is the radius and alpha is the angular acceleration. And then you can have another situation that the pure rolling is taking place, but sliding is impending, that means sliding is about to begin. In that case, F will be exactly equal to mu s times n, and you will have A is equal to r times alpha, where alpha is the angular acceleration and r is the radius of that disc. Then you can have the third condition in which there will be rolling, but there will not be any sliding, and sliding also, both will go simultaneously. In that case, what will be the equations? One is that F is equal to mu k times n, that normal force and tangential forces are related by kinetic coefficient of friction, that is mu k, and A and alpha are independent in this case. We will not have any relation between A and alpha. Now, when it is not known whether a disc is sliding or rolling, then what should we do? We should first assume that the disc rolls without sliding. So we assume that the disc is rolling without sliding, so pure rolling motion is taking place. Now if F is found smaller than or equal to mu s times n, that means our assumption was correct. Now if F is found larger than mu s times n, then the assumption of pure rolling was incorrect and the problem should be started again, now this time assuming that rolling and sliding. So the equation also, the expression for force will also change, and F will now become equal to mu k times n. So this is, now let us solve a problem on rolling. Now this will be like this. I have shown here a inclined plane, this is at angle theta, and this is the metal hook G with a radius r that is released from the rest on the theta incline. Now if the coefficient of static and kinetic friction are mu s and mu k, then we are we have given that you determine the angular acceleration alpha of the hook and time t for the hook to move a distance of s down the incline. So this is shown here in the figure, this one. So now if it is a hook and it is a hollow, that type of thing here, that then it's a moment of inertia about g is given by mass times distance square, radius square, mr square. Okay, we may make use of this relation. Now just see. Now if we make the free body diagram of this hook, you are having a force F, friction force which is upward, and then you will have a normal force N, and then you have got a mass, its a weight is passing through the center of gravity, this is mg, and then this is A, and this is alpha, and this will be y. So the counterclockwise angular acceleration requires, you have got counterclockwise angular acceleration because this part mass is coming down here, so acceleration is counterclockwise. So you require a counterclockwise movement about g, so that means F must be upward. So whatever direction we have shown here is correct actually, that means here from, so it is counterclockwise. Then we make the kinetic diagram, in that we just show that mass times acceleration which is in the direction of inclined plane, and that Ig times alpha. Now assume that hook rolls without slipping, so that A is equal to r times r alpha, that equation is valid. Now you write the basic equations. So three equations of dynamics are written. One is that relating the tangential force, so mg sin theta is the force due to gravity minus F is equal to mass times acceleration, that is this one. Then you have got n minus mg cos theta is equal to 0, that is the normal direction, that is also there. The third is that moment, that mg is equal to I alpha. So therefore what happens, this is F into r is equal to mr square into alpha, that has been obtained by taking moment about the mass center m. Now if we eliminate F between first and third, f is appearing this thing, we eliminate f because we don't know this f, what is that. So we get then a is equal to g by 2 sin theta, eliminating that f is equal to this one we can put, and of course n is equal to mg cos theta, that thing we are not using right now. So we find out that eliminating from this, we have eliminated this f and we put this, then we will be obtaining a is equal to g by 2 sin theta, and f will be equal to mg sin theta minus m g by 2 sin theta, that means mg by 2 sin theta. Now from the second equation we get n is equal to mg cos theta. So the limiting force is f max is equal to mu s times mg cos theta. This point is mg cos theta. So we have to see that whatever that force we have obtained, that is mg by 2 sin theta, it should be more than mu s into mg cos theta. So therefore in this case, so in case that you get f max is smaller than f, then the assumption of pure rolling is wrong, that is the this one. And in case you get that, suppose you get that f max by that thing, so it is mu s mg cos theta, and if it comes out to be, because this is the maximum possible value, so in that case a will not be equal to r alpha, and you will be getting f is equal to mu k times n. You have still the relation between the force and the normal reaction, that is mu k mg cos theta. So this is, now you put this in the first equation, mg sin theta minus mu k mg cos theta is equal to mass times acceleration, and in this case the acceleration will be g sin theta minus mu k times g cos theta. So you get a different type of this one, and we can of course use that sigma mg is equal to ij alpha, that means we can write mu k times mg cos theta into r, that will be equal to ig times alpha. R alpha is equal to mu k mg cos theta r divided by ig. So that way we can find out angular acceleration and linear acceleration both, although they may be unrelated. Now the time required for the central g of the hook to move a distance s from the rest with constant acceleration obviously can be found by t is equal to under root 2s by a, where this one 2s is this one distance. So because this is simple formula, s is equal to ut plus half at square, and this portion is being 0. So you know t is equal to 2s by a under root. So that means once we have found linear acceleration, be it in pure rolling motion or be it in rolling cum sliding motion, we have found, and therefore we can always find out time, and that is under root 2s by a, and we can solve this problem. So that way, by applying these basic equations, that you know what is that, f net is equal to mass times the acceleration of the center, that is the vector equation, and also that m is equal to I times alpha, m0 is equal to I0 times alpha. By applying these equations, we can solve any problem of kinetics in the plane motion.